welcome everybody to Supreme Sight. Really, this is interesting animal eyes and hopefully what they can teach us about human eyes, but a lot of just adaptations in the animal world that are unusual or that sort of reflect back on what we know about our anatomy and physiology and looking at the optic system. So I'm James Major, Retina Consultants of Texas. And next slide. Here I got it, I think. There we go. And so here's Retina Consultants of Texas. Again, we're the largest retina group in Texas. We're also the largest retina research center. We combine forces with a powerful group in San Antonio, formerly Retina Consultants of San Antonio, now Retina Consultants of Texas, and we were Retina Consultants of Houston. So both of us are now Retina Consultants of Texas, both San Antonio and Houston joining forces. And there are 20 of us sort of all over Houston and all over greater San Antonio, including the Hill Country, which I'll show you in a second. So there are our offices. Basically, if you throw a dart anywhere in greater Houston, around the Beltway, North, 610, centrally, we're sort of everywhere, including East Texas, Livingston and Lufkin. We have newer offices in Pearland, a brand new office in Memorial on I-10 and Gessner, and also our flagship office is Bel Air on Newcastle and Bissonnette. And we still have our old space at Scurlock Tower, which is next to Methodist at the medical center. But basically all the sort of suburbs of Houston, any areas. And then here's San Antonio. So you see they have Stone Oak, New Braunfels. There's even Fredericksburg and Kerrville out in the Hill Country, Bernie, Seguin, Alamo Ranch, and of course the medical center. So same thing, pretty much all over, especially north into town for San Antonio. I have absolutely no off-label discussions, no financially relevant disclosures, no IRB approval, no human studies. These are all animals for fun. I was perhaps paid for by the Raptors for Vision Political Action Group. Just kidding. There's nothing to disclose this time. So this talk is really a letting my worlds collide. So for many of you who don't know, I'm basically a glorified bird watcher and sort of have been for my life. So my PhD people say, oh, did you work on molecular biology or did you work on, no, the answer is I worked on ornithology. So I went to University of Texas in Austin. I got my master's and PhD on a genetic hybrid zone in a bird and how the hybrid zones, so it was really population genetics, but it was old school sort of ornithology. Then I flipped gears completely and went to medical school. So I let my worlds collide Seinfeld style. And so this is a picture, that beautiful head of hair is me. So this is my dad and I as a kid walking in the Everglades, and sort of as a young boy and growing up, I bird watched all the time is what I did with my family and what I did with my dad. So everywhere I went, I took my binoculars and went birding. So there's a picture of me as a young boy with my dad, full head of hair, binoculars, of course. That continued in a later life. I went on a medical school trip. This is like 15,000 feet. This is in Cotopaxi in Ecuador. And there's Andean gulls behind there on that high Andean lake. Again, my binoculars. Much to the wife's chagrin on the honeymoon. This is Kenya, and this is Kilimanjaro in the background. There I am, dorky binoculars right there. And you can even see a zebra off in the back left. So basically birding wherever I go. So when I was a resident in Miami, I knew the person who owned the Miami Museum of Science or ran the Raptor rehab program. And I said, we have this new machine that's a spectral domain OCT machine. It wasn't even commercially available. They had a time domain, the old school OCT machines. And this was the new spectral domain OCT. And it was only experimental, not commercially available. And I said, I'd like to take, birds I know have great retinae, and I want to really see if we could try to image that. So this is a broad-winged hawk that they brought in, and the broad-winged hawk was blind in one eye. Although the eye looked externally normal, it wasn't, there was no signs of any trauma. Someone found it on the road, I think. It was there. So I said, bring that bird in and we'll see what we can do. Well, they also brought in a barred owl. So this is the woman that ran the Raptor rehab center at the Miami Museum of Science. And it turns out, dilating birds, as we'll find out, birds have skeletal muscle in their iris. So I said, what are we going to do about dilating their eye? Dilating drops are not going to work. Long story short, this barred owl was tame and was sort of born in captivity. So there was nothing wrong with it. But if you scratched its neck, it would just sit very calmly, like a dog would just sit very calmly at the OCT machine and would let you turn down the lights. The pupils got real big and we could scan it. And surprisingly, we could gently turn off the lights and hold the bill of even the hawks and get a pretty motion-free scan, as opposed to giving them any inhalational anesthetics and all this other thing. So it actually worked out pretty nicely. So here's another, what you see there is the spectral domain OCT machine, which now is a small box that everyone has in their office, but this is before it became commercially available. And again, this was 2008. And then I'll show you those images. And flash forward, I've sort of continued that interest, and this is our Woodlands office. And this is the same thing. This is the Defenders of Texas Wildlife, which is in the Woodlands area. This is a great horned owl that got hit by a car and had damage to the left eye, as you'll see. And they're at the Heidelberg Spectral Domain OCT, same actual machine. And this was a screech owl too. So we brought in these birds and some other hawks and tried to image their retina. The great horned owl is a great story because that bird only had one eye, but they said, we know, is it permanent? They wanted to know, is it permanently damaged? Or can this heal itself, and will this bird be able to go back into captivity? And that bird actually, we did some serial fundus photography and OCT imaging, and it had a big vitreous hemorrhage and what appeared to be some like peripheral areas of subretinal fluid. Anyway, over a period of say 6 months, or perhaps even longer, that blood cleared. The bird seemed to be able to see well. We could never tell, but it probably had some pretty good functional vision, that left eye. And they ended up releasing that rehabbed bird back into the wild because it was a wild-caught great horned owl that you see sort of on your top left. And so it resulted in the bird being, sort of released in the wild. So these were the very first images ever, in vivo images, which look like histology for raptors. So these were my initial studies, and you can see birds have a fovea centralis. And there's, when you look at the little histology, there's a diagram of a sort of shallow human-like fovea. And then above that, that very steep, it's called convexiclivate fovea, has, we got an image of it at least. And they have this weird, unusual vitreoretinal interface. And this was that broad-winged hawk that I first showed you. And this is one of the images we got. You can see normal appearing retina to the left, and to the right, cystic changes, maybe a chronic RD with chronic cyst. Clearly some pathology there. The OSIS and sort of RPE is gone. So we said, look, this bird, for whatever reason, has a retinal detachment. And we even found, you can see what appears to be normal peripheral retinal broad-winged hawk anatomy, and then what appears to be chronic subretinal fluid, like a chronic RD. So that bird would remain in captivity. But these were the very first raptor in vivo OCT images that were ever done. And this was 2008, 2009. So that sort of leads us into this. And so what we'll really talk about today, and we'll get back to birds, of course, because that's my passion, my fire, but we'll talk about mutants first. So these are interesting adaptations. So everybody knows about X-Men. You have a mutation and you have wings on your back and you can fly. You're Magneto, you can control metal or whatever you can do. So these are X-Men, but the story is not correct. Let's talk about color vision. I'll explain why. So on color vision, as a recap, remember the cones, the photopigment cells are carried on the Y chromosome. So remember, males are XY, females are XX. And about 8 to 10% of males are red-green colorblind. And again, that is carried on the Y chromosome. So it's just simple sort of Mendelian genetics. And females carry the cone photopigment. So trichromats are the normal. You have a short, medium, and long detecting wavelength cone light, or really blue, green, red, right? And so you have females have an extra X. So if one X is bad, the other does the trick. So females are typically carriers, and they give rise to other female daughters that are carriers. But the males, because they have one X that is bad, doesn't carry the photopigment, the red-green color, let's say, and the 1X, carries it, and the Y does not. It's only carried on the X chromosome. Well, that leads us to, that's dichromat. So in other words, if this would be one of the 8 to 10% of males who's red-green colorblind, we would see the color with normal vision, like you see that rainbow on the left and the right. And, the red and green are just sort of washed out. So there's regular Bambi and washed out Bambi. But the story is wrong. It is not X-men, it is X-women. So remember I said it was carried on the X chromosome. What if females, if you had a mutant extra cone on your X chromosome, you could result in a tetrachromat, or carry 1, 2, not 3, but 4 color photopigments. And is that true? Does that exist? The answer is yes. They've identified several females. There's UK, there's some in the United States. There's two that I know of in the United States that I've seen written about. So these very rare tetrachromats have an extra orange. They essentially have an extra photopigment between red and green. So ordinary people, we see 5 colors in the rainbow, right? Red, yellow, green, violet, blue. They see 10 colors in the rainbow. Regular folks can differentiate 1 million colors. They can differentiate 100 million colors. It's incredible. So their color vision is like that of a bird. It's much, much, much better. And the two females in the United States that I know both worked in visual industries. One was an interior designer or decorator. So someone would be like, oh, throw that gray pillow over there. And they'd be like, actually, it's a mauve shade of gray. And they could take all these color patterns and look at what you needed in your house, you know, what for me would be a gray or a white or an off-white or a cream. They saw like 10 different kinds of cream and could match them up. So there was that person. And the other woman lived in Washington State, and she'd say, you know, the snow is starting to melt. And they were like, how do you know? Do you see that? Or is it a weather change? She could tell by looking at the river. She lived near a river, and the river would start to produce silt from upstream that to normal people, you know, obviously you can tell when it's filled with silt, but she could tell the first sort of a little bit of gray that appeared, and the colors by changing the colors in the river, she could change, sort of look at seasonal activity, especially snow or silt in the river that other people couldn't detect. It was pretty amazing. I've seen a little video on it. So X-men do not exist. X-women exist. Mutants, we will not hunt them down. Okay, switching gears. Fish. So I got a couple slides on fish and basically why fish have weird eyes. So we'll take some unusual animals. So fish are obviously very thin to move through the water, right? And the key point here is if you live in the water, your cornea is the same index of refraction as water. We live in an air environment, right? And the index of refraction of our cornea does most of the focusing of light on our retina is done by our cornea. You've all heard that before, many times before. If you're in the water though, the water basically, index of refraction of the water and the cornea are basically equal. So you cannot rely on your cornea. So what they have this neat lens that protrudes through what's called a piriform pupil. And piriform means pear-like. So that's why the little picture of the pear is there. So instead of having a round pupil like we do, they have a pear-shaped pupil. When we move our lens, if someone brings up and says, look, mom or daddy, and they bring up the book right to your face, and when I was not 50, accommodate on that, your lens is deforming, right? You're stretching it with the zonules, but they actually take their whole lens and move it from one side to the other. So they can move their lens forward or anteriorly and move it posteriorly. So it's not deformation of the lens, making it fatter and skinnier. They actually move the whole lens. And they have this neat thing called an aphakic space. So this would be, imagine a left eye of a fish, and it's hard to see, but there's a little gap space right there where there is no lens. And the rest of the lens is sort of backward. I've sort of highlighted it there in red. It's a little crescent. And so what they're doing is taking their lens as light enters, you can see this aphakic space, and they have their fovea is extremely, extremely temporal. It's very anterior located, not in the back, because they're so skinny that the light is coming in essentially, from the front, and they can take that from anteriorly, and they can take that lens and move it forward and backward, not deform it. But that is their aphakic space just in front of the crystal lens. Piriform, that's where the name piriform shape or pear shape gets from. Marlins are neat. Everybody knows what a marlin is. So marlins are the huge predatory fish. They are not mammals. They operate at deep, cold depths, right? But they're cold-blooded. So here's the problem. If you are hunting big fish like a small tuna or some kind of salmon or some kind of fish that's very quick and lives very deep, the temperature at deep water depths, especially in cold water, is barely above freezing. Let's just say it's 40 degrees. So if you're down at swimming actively at 40 degrees and you are cold-blooded and there's no sun, like you would warm yourself on a rock like a lizard or a snake, what do you do? Because you're the hunter, so you actually actively have to keep hunting. So this brings us to the problem of brain freeze or slurpy head. So the water temperature at 600 meters is 2 to 8 degrees Celsius. You know, it's roughly 40, 45. So what marlins do is they have the most enlarged extraocular muscles on the planet. Their extraocular muscles are big, beefy, huge things. They have no actin and no myosin, and they're all mitochondria. They have their mitochondria in a marlin's extraocular muscle has 3 times the amount of mitochondria that a muscle cell does. And that is for one purpose, and that's to generate heat. So their muscles do not, their eye is so large, it does not move, but it generates heat. The heat then dissipates to the vascular plexus around the brain and the eye as best they can. So at least their front part of their head and their brain and their anterior portion of their body is fueled and retains heat because of their extraocular muscles. So they act as superheaters. So the brain is 25 degrees, whereas where they're swimming is say 4 or 5. And this is for deep water hunting. You can see, so that where it says ON, that's optic nerve, that's the eye, and then all that beefy tissue there, see, that's the superior, that superior rectus is a giant chunk. And when you get in, their superior rectus is basically bigger. If you look at the CT image on the left, that large thing you see in the center is their superior rectus muscle. That little thing you see on top of it, unfortunately for a marlin, is their brain. Not a good idea to have your muscles larger than your brain, but that's okay. Stargazers, another weird fish. So that's done something with their muscles. So stargazers, they're like a flounder, basically. They live on the soil, Astrocopus. They sit on the bottom motionless, and they wait for other fish to come by, and they snatch them up with their big mouth. So they don't need their extraocular muscles for movement. They don't move their eye. They're fixed, and they continually look up. So during development, their extraocular muscles grow to be huge, 6 times the size that they normally would be. They have now infused it. It functions as an electric organ, stunning predators. So you're walking along on the beach in Galveston, you step on a stargazer, you get zapped with 50 volts from their extraocular muscles. Thank you very much. So no movement, they are a voltage delivery organ. The final weirdest fish is the anableps, or the four-eyed fish. And they actually have these at the Houston Zoo. They're these very, fairly small fish. They live on the surface of the water, and they live half on the surface. So their eyes are half out of the water. You can see in the picture on the right, half out of the water, half underneath the water. And they catch little insects that fall into the water and snap them up from the surface of the water, bugs and things that they live in swampy areas that fall off trees and whatnot. And so their eye anatomy is very cool and ridiculous. So they have, their iris has this pigmented finger to separate the halves. So like 2 halves coming together, their iris sort of joins hands and gives them essentially what is a superior pupil and an inferior pupil. Well, the inferior pupil is where water, light from the aqueous environment, is going to come up to the superior retina. And the flip is true. The superior pupil is where light from the air comes down to their inferior retina, right? And so their interesting thing about them is their lens is rounder. It is not a sphere, but it's a rounder portion along the lower aquatic axis. In other words, the red line that you see is light coming from the water into their superior retina. And remember, we talked earlier that the cornea doesn't do anything for you basically in water. So the cornea does nothing. You need the lens to do most of the focusing of light on your retina. So light enters the lower pupil from the bottom, goes through the longer axis of this lens, this asymmetric lens, and is focused in the far periphery of the retina. Whereas light from the air comes through the upper pupil, goes through less of the lens and more of the cornea. If you notice, the cornea is a little thicker here, the blue, than it is the red, and then gets focused on their inferior portion of their retina. They also, their lower retina has more bipolar and ganglion cells. They actually have 9 cones in one rod. So their color vision is probably off the chart. Their air color vision is probably great. So we think, based on their eye anatomy, that they have great vision for the air, for seeing little bugs and things like that, and approaching predators from the air environment. But underneath, their vision from the water is really probably just to see something coming at them from below. I mean, they can see probably better than we can underwater, but their murky, dim water vision is probably a protection against, predators. So it probably looks something like this. Imagine when you have your mask on and you're half in the water, half out. So they probably have great vision up top, and maybe, you know, maybe even not that clear down below, but that's what their whole world looks like all the time. Anableps, the four-eyed fish. Weird. So I will ask you this, Gary. Are you ready for this very important question? Why do animals have eyeshine?
So people get eyeshine when you have a flash picture at a party. It's light bouncing off your retina, which is orangish red. And then deer and other animals will have a reflective layer. I think it's the tapetum, is that right?
Yeah.
And so light is actually reflecting off their retina. And that also gives them twice the chances to capture photons in dim light. The rod can pick it up going into their eye, but then it bounces off the tapetum and comes back out, and it has another chance to be detected.
Yes, Dr. Lane. The answer I was going for is, so in Texas, you can spotlight them better. No, that's a joke. Yes, you're 100% correct. That is the Texas answer. But yes, exactly correct. So eyeshine. Humans have the red relief effects, like Dr. Lane talked about. Nocturnal animals have a guanine and reflective deposits in their choroid, which, exactly as you mentioned, is called the tapetum lucidum. And what Dr. Lane was mentioning, imagine the light going in. Those little yellow specks are your rods and cones, probably rods in this case. The light goes in, misses a rod, a photon of light misses a rod in the retina, hits the choroid and the guanine deposits in the back of it. And it's beautiful when you dissect it. It's like a shiny back of a camera, re-reflects, and then has a second chance at hitting light, exactly like Dr. Lane mentioned. So does it give you a super crisp image? Probably not, but you're basically gathering every photon of light you can in the dark, and you probably can see very well. So it might not be super crisp, but you get a second chance at light. And when you shine the light in your eye, like a dog or a tapir or a raccoon, and they have different colors too, and even birds have it, you can see the eye shine back at you. So there's a guanine deposits in the layer, and that's called the tapetum lucidum. Yes. So this takes us to the avian eye. So bird eyes have sort of the best vision on Earth. They're known for their eyes. Mammals were probably known for our hearing, but the avian eye, especially raptors, and we'll get to those, have the best eyes on the planet. So they have, they have to fly. So you can't have bad vision if you're going to be flying around at 60 miles an hour. You got to be quick. You got to see well, especially if you're going to catch something or be caught. So we'll talk about all those things. Typically the bird's eyes are very large, and they outweigh the brain. And again, remember we talked about in air, the cornea does most of the focusing ability of the bird's eye, unlike water where you need your lens, and their color vision is off the chart. It's fantastic for most, especially raptors. So color vision birds, we talked about this a little bit in the humans, but almost all birds have 4 cones, and some even have 5. So they're pentachromats. So they sort of act like those mutant females that we talked about earlier, and probably can see, 100 million colors to our 1 million. So when we look at a tree in the spring, we're like, there's a tree, it's green. Got some dark green leaves, has some light green leaves. When they look at that tree, they see dark green, a little less dark green, light green, a little darker green, medium green, all the different greens. And that's important because they can tell new buds and new leaves from old leaves. So where the insect's going to be, where the fruits or possible flowers going to be that they're going to eat. Also, we see a minor bird at the top. It looks like this. There's a very good chance, because they see into the infrared spectrum and ultraviolet, that they see a much colorful bird. So birds that to us that look like a shiny grackle probably look very different and more colorful to other birds. They have these neat things called oil droplets. So on the right, you see a cone, a typical cone cell with the visual pigment at the tail, and they have a little droplet right in front of it. And these have been highlighted here in this middle picture. They think, they don't know the exact reason for the oil droplets, but we believe it enhances color and acts as a magnifying glass for photons of light coming in, thus enhancing color vision. So they're oil droplets within their actual cone cells. It's really neat. Also, the density is different. We have 200,000 photoreceptors per millimeter of retina. They have 1 million, so 5 times the amount of density. Also, in humans, if you go along the chain of command from cone to bipolar cell to ganglion cell, going back to the optic nerve, we probably have, I'm making these numbers up, hundreds of cones to 10, 20, 30 bipolar cells to one ganglion cell. They have one cone, one bipolar cell, one ganglion cell. So there's a 1-to-1-to-1 connection in terms of visual acuity. So it's not just the color, but it's the way it's done. And then Gary, throw out or tell us a little bit about, you mentioned earlier the double cones and anything else you know about cones that you'd like to add.
Well, one thing is interesting is all birds have 4 pigments. Fish, reptiles, and probably dinosaurs did as well. And then lower mammals have 2. They probably went through the nocturnal phase. And so lower mammals have 2, and then primates and humans, they duplicated the X chromosome. So they're back up to 3 again. So you can kind of see these stories of how these animals evolved through their cones.
Super interesting. Here's a little bit of an owl eyes. Everybody's seen an owl and they twist their head around. So they can probably turn their head. They can't spin it all the way around, but they can probably do a 270 versus a 360, right? They don't want to snap their spinal cord. But they have our axial length is roughly what, 23, 24. Theirs is 34, so it's much longer. It's a very large lens and a large anterior chamber, and they have these scleral ossicles that keep it together. Again, there's a picture of their eyes, and there's a picture of their brain. So their eyes are larger than their brain, including, look at the size of their lens is, basically put the 2 lenses together, it's not that much smaller than the brain itself. So the owl eye is neat because we all think of a fovea, and at night when you go out and you're looking at a dim star, I remember as a kid, I always wondered why when I looked right at something, it went away. So you go out at night and there'd be a dim star and you see it out of the corner of your eye and you're like, oh, there it is. And then when you look right at it, it goes away because you're putting the image on your fovea. A human fovea is cones, and so there's color vision, not adaptive. There's really no rods there, so the image goes away. So the best way to look at something at night, if it's dark, is to look ever so slightly off of it. Well, not in an owl's case, but an owl, their fovea is not filled with cones like ours, but rather with rods, which is really unique. They don't have any room for extraocular muscles, so their head turns 270 degrees. So that space is filled with essentially eye and not muscle, and that's why they turn their head. They do not look up and down, left and right like we do. And they have 60 degrees of stereoscopic visual field. There's a group of birds called, also that middle picture is showing, I didn't have it on here, but that's a nictitating membrane. It's also called a third eyelid that essentially washes away. Raptors have this, and on the birds, reptiles too. It's essentially a third membrane that comes, the nictitating membrane that comes down and blinks for them essentially without the blinking of the outer lids. There's a group of birds called caprimulgids or goat suckers. You know them as whippoorwills, chuckwills, widows, nighthawks, which are common around San Antonio and Houston. They have nocturnal tubular eyes. And there's another group within this that have these really neat mechanism to prevent becoming prey. So these are what the night jars look like. There's a whippoorwill, in South Texas, one called a poorwill, but these sleep during the day and they're active at night. They catch moth and insects on the wing. They're very, very cryptic and hide in dead and leaves and things like that during the day. And they hunt in the forest or over fields at night. And if you look really closely at the poto, which is one of these, can you see the little slits in their eyelids? So that bird looks like a dead branch sticking up, this poto. And if you notice 1, 2, 3 little slits in the opening, these are sort of connected to motion detectors on their retina. So if you were to say you see them and walk up and try and grab them during the day, they at least, even though they're sleeping, so to speak, they at least have enough motion detection. If something sort of flashes in front of that, they will fly off or wake up. And so cue the Metallica, sleep with one eye open, enter Sandman. Woodcock is another interesting bird. Woodcock is interesting, not necessarily because of their eye adaptations, but where their eyes are. So a woodcock eats earthworms. They stick their sensitive bill down into muddy soil and eat earthworms. You also see them, on hunters' guns, and they frequently decorate sporting items for the bespoke huntsman. They're very wary. They're hard to spot. they have very large eyes and they're set very high in their head if you look at them. And what they're really doing is getting a 360 visual field. So they don't want things sneaking up on them. They don't necessarily need binocular vision in front like we have. They want their eyes up and to the side. So they're probing, their bill is doing that job. They're not looking under the soil, they're feeling for earthworms. So the baseball analogy is the pitcher's on the right-handed pitcher is standing on the pitcher's mound pitching and can basically see the second baseman around him and all three bases. So it prevents you from being predated upon, basically. Here's the age-old question that you guys have been asking yourselves and cannot sleep at night. Why do woodpeckers not get a retinal detachment? Now, Gary, do you have any insight here before I get into it? I have slides on it. Does this keep you up at night?
I've worried about this a lot, so please tell me.
Yes, I will. So if you think about it, a woodpecker, you've seen them, and especially if they land on your building and they're wasting away at your metal, they hammer it 20 times per second sometimes. It's like you can barely see their head. They do this 12,000 times a day. So it'd be like us walking up to a wall and at 16 miles an hour, so banging our head as much as we could all day. So they have to have a way to protect their eyes, basically. And they have several functions. Number one, they have a thick, bony skull with spongy bone, not necessarily hard bone, that helps to absorb some of the impact. They don't have cerebrospinal fluid around the brain like we do, and they strike perpendicularly, but they have a very small brain, which I guess helps. And one of the neat things they have is number 6 and 7 are maybe the most important. They have a shock absorbing tongues. Instead of our tongue comes from the bottom of our mouth and comes out, their actual tongue goes around their eye here in a loop and then out. So when their tongue contracts, it actually, like a vice grip, houses their eye and keeps it from vibrating. And the last thing they have, there's this thing called a pecten, which is a super highly vascularized structure. Especially birds of prey they have an avascular retina, because when we have vessels that occur in our retina. And so when you think about it, if you actually have a fovea that's behind your vessels, as photons of light come in the eye, they're actually striking, and you're missing some photons. They're striking the vessels in front of it. Birds do not have that. They have their retinas completely avascular, and we think the way they get blood flow is this pecten that diffuses oxygen into the vitreous cavity, and that's how they get their oxygenation levels. So this pecten, and maybe from the cord behind, so the pecten looks like an accordion. It's very, very highly vascularized and has a huge surface area. But they can take that pecten and fill it very quickly as they hammer, so it fills the eye from within. The loop-like tongue closes the eye from without and essentially barricades the eye pressure-wise from within and from without, and compresses the eye, thus preventing the retinal detachment. So we're on to raptors. So raptors are the ultimate vision, especially diurnal raptors, right? Most birds we're talking about hawks, eagles, and falcons now, basically. So why is their vision so good? So we'll talk about birds of prey, which is sort of the ultimate vertebrate adaptation in terms of eyes. So we think an eagle vision is about 24, not 2020 or 2015, but 24. In other words, what we can see basically right in front of us at 4 feet, like your hand out here, they can see at 20 and probably even longer. And that's not even the color, that's just the sort of visual acuity. And there are many other adaptations. Color vision we've discussed. One of the neatest things about a bird of prey's adaptations to their really neat eye is they have instant LASIK, basically, instant LASIK surgery. So we do not move. Our cornea has a fixed index of refraction. So we walk around and that index of refraction, we change it, we give somebody LASIK, we put a contact lens on it, whatever. They have a muscle called Crampton's muscle, which is a skeletal muscle, and you can see it in the histology diagram here. It comes out near the ciliary process and goes out into the cornea for 360. So they're instantly changing the index of refraction of their cornea, which is amazing. So it's like having highly adjustable LASIK surgery all the time, super quickly. Their iris and their ciliary muscle is skeletal muscle, which is much, much quicker than ours, so it reacts quicker. And their accommodative power, looking up close, ours is, let's say, 15, 20 diopters. Theirs is 70. So just a couple of those things. And you look at their retina, their choroid is 3 or 4 times thicker than ours and super highly vascular. So maybe that puts them at risk. If you're a stressful raptor, perhaps you get central serous chorioretinopathy. They do have pachychoroid. Maybe it's holiday time and they don't have the rats that they used to. So they get very stressed and they've been taking steroids and they've been smoking and they get subretinal fluid. No, I'm not sure about that. But their choroid is 3 to 4 times thicker. And what's interesting about their choroid, there's actually muscle in their choroid. So imagine, well, we can't move our retina. Well, you can change the index of refraction of your cornea up front. You can also take the choroid and move the retina forward or potentially back. So just like making someone myopic or hyperopic, it's like glasses from the rear. So you can move your retina forward and back with a muscle that's found in their choroid. The retina is much, much thicker than ours. They have more bipolar cells, more amacrine cells. We talked about the 1-to-1-to-1 connections, cone to bipolar cell, the ganglion cell. And then they have this neat, what's called a convexiclivate fovea. So our fovea is not as steep as this, but they think the purpose of this convexiclivate fovea, it adds about 10% magnification. So imagine light coming in, it actually diffuses out over their fovea in this region and probably gives them another 10% magnification in addition to the other adaptations. And one of the really neat things is they have 2 foveae. They have like a hawk or a bird of prey has a nasal fovea and a temporal fovea. They have 2. So imagine the human analogy would be you're reading a book like this and you're putting the image on your fovea and you're reading. Well, someone else takes another book, puts it next door or on the side. So here's your one book. You got another book over here, off to the side. You could read that book also. So you could read the book in front of you and you could perfectly well see the book that's off in your peripheral vision. So imagine having that, we take it for granted because our peripheral vision is there, but if we look at it, it's not clear. Theirs would be perfectly clear. So fish, fish, reptilian, and avian fovea tend to have this this steep fovea, what they call our convexiclivate fovea, which magnifies the image. Whereas the primate fovea, much less so. And there's a picture of the 2 fovea there, the central and the temporal, and I'll show you why that's important. Gary, anything to add so far? Dr. Lane.
That's awesome. I never knew that. That's amazing.
Yeah. And then here's another problem that they've dealt with. Well, you can have the best vision in the world. If I have fantastic vision and I can see, so they think that birds of prey, when you see, you're driving in the winter in San Antonio and you see a Harris's hawk up on a telephone pole and they're scanning a field. Well, you look at that field, you just see brown grass. The Harris's hawk, in addition to having better vision, maybe see a rat, they see in the UV spectrum. So rodent urine gives off UV light. So it's a railroad tracks of old, medium, and fresh urine all over that field. So we think, even if they have good vision, how would you catch a rat in that field? Urine might be one of the answers. They can see, oh my gosh, there's fresh urine right over there. They hone in on it because they can see it. We cannot. And then they focus in on that and hopefully catch something. But if you can have the best vision in the world, but you need to process it quickly, right? So you've seen these pictures of birds of prey that are unbelievably fast. They even will put a cone, they slip through the cone, they're crashing through trees, they're going through tiny little spaces at what seems like 100 miles an hour. It probably is 50 or 60 miles an hour. So they have to process the image in their retina much more quickly than we do. And this is called flicker fusion rate. To put it in perspective, the human flicker fusion rate is 55 cycles per second. Theirs is 175. So what happens is the image is processed in the retina and much less in the brain. We see something, we think about it, oh, that's a bear. I'm going to secrete some epinephrine and I'm going to run, or at least run faster than the guy next to me. Whereas they see a bear and they're gone. There's no third-party brain processing. It's retina, bear, gone. And so they can detect very, very quick movements. And flicker fusion rate, the easiest way to describe it is the way you process an image. Old school movies. Have you ever seen the movies or where you take a deck of cards and you go through it, it looks like a horse is slowly galloping, and the faster you deal through that deck, the faster the horse runs? Or the old movies had a slower flicker fusion rate. It appears as though things were moving in slow motion. So birds of prey have the ability to, quote, slow things down. And what's interesting about it is they think that really good batters and athletes have this ability as well, have an improved, faster flicker fusion rate. So you've always heard athletes say, oh, when I made that winning catch and I caught the touchdown with one hand, it looked like things were in slow motion. I saw the ball spinning and I could see the laces on it. Or when someone's batting, they can detect a slider versus a curveball versus a changeup versus a fastball that looks like things, quote, slow down. Athletes probably have a different flicker fusion rate, and birds have this to adapt. It's interesting. These are the first images that we got on the birds of prey on their phobia. So there's that convexy clivate, that very steep phobia, and there's the shallow phobia. And when you look at it in real life, there's the pectin, that sort of black silvery thing that again is vascularizes the retina. They have the nasal phobia, which is the deep phobia. You see the one at the top that just says phobia. And the shallow phobia is the temporal phobia. And the way they use it is like this. When they're flying around, so let's say I'm a peregrine falcon and up flies a partridge and I am flying, I climb above it. I'm now stooping and attacking that. I'm above it and I'm flying now over 200 miles an hour, faster than free fall. And I will hit that bird from above. So things are obviously happening very quickly. When they're tracking the bird, they put the image on this nasal fovea, which is their better seeing fovea. And let me see if I can flip it here. There we go. So imagine here's the bird flying. So the things that are off to their periphery, they're using this temporal fovea. So look at images A, B, C, and D on this eagle that's about to grab a fish. So they're probably, as the bird comes in, he's using the more convexy clivate, that temporal fovea. Right at the last second, which is image E, they look down. And because they have to grab the fish, they can't not look at it. So they actually switch the image from their temporal fovea to their other fovea, their central fovea, and still get binocular vision. So this is one of the advantages of having two foveae. They switch it. So the same fovea, the better fovea, so to speak, is probably being used in A, B, C, and D. When you reach down at the last second and look down and catch that fish, they switch the image, because if they didn't have that fovea, they would lose a second or two of where is that fish or where is that mammal, and enables them to catch prey. This is also seen in Eagle Rare single barrel Kentucky straight bourbon whiskey. Look down at that eagle. That eagle is using he's about to catch the fish, just like image E, and has switched his foveas there. So, Gary, anything else that we need to add about birds or mammals or anything?
That was a great talk, and that bourbon looks really good.
Doesn't it though? The holiday times are approaching indeed. Let's see here. So that concludes our sort of interesting animal talk. Please stay on, and Gary's there to answer. I can too. We both can answer any questions. Dr. Wynn is here too. I see her, B. Wynn, with us. So a special thanks. There's a really neat book out called Evolution's Witness, and it's by Ivan Schwab. And it came out about, I guess it's been that long, about 8 years ago now. But he was nice enough. He contacted me and said, hey, I really want those raptor images that got OCT on. So he put them in his book. And so fish, reptiles, if you have any interest whatsoever, it's basically unique eye adaptations throughout the animal world, which is really, my partner, Richard Fish, many, many years ago, gave a talk similar to this. And this is comparative ophthalmology talk. So I definitely am indebted to him and used his notes as well. So Dr. Fish has always long been interested in this topic. And then lastly, Sarah Barbatano and Mackenzie, we've done many, many CEs this year. They're all put on by Sarah Barbatano and her and Mackenzie and others that help. And so I wanted to thank her for working so hard and doing such a good job on all these CEs, whether they involve Raptor Retinae or they involve anti-VEGF and macular degeneration and diabetes and research. Sarah does it all. So thank you, Sarah, very much. And we'll stay on. And so again, answer any questions. I'll stay on for a while. And I think we're on time. Thank you for allowing me the privilege of presenting. I love letting my worlds collide. And it's really fun for me to do this talk. And I enjoy it so much. And so join us on the image portal. You sign up, you complete the short registration form, you confirm your email, it takes 2 seconds, and then we get the wonderful colored image that we can share in a HIPAA compliant fashion back and forth. So easy. That's been around for a while. Call us. There's someone always on call. There's a fax referral number, refer online. And thank you for participating. You're wondering about your CE. Well, you've been captured by Zoom. You're all set. You'll get an hour from the TOB, and stay tuned for the upcoming 2022 schedule. But Sarah, any word on the month that we will start one perhaps?
We have our list, and they just need to stay tuned.
We have our list, and stay tuned. Happy holidays and happy New Year's, everyone. Stay safe, and thank you so much. Really appreciate it.
James, I have a question for you.
Hey, I think, is it just us now, or are there?
There's still people on.
What?
There's still people on.
Oh, there's still people in. Yeah. Oh, yeah. Go ahead, Gary.
I was just going to ask you about the double cones. Does anybody know much about that? Some of the birds have double cone cells.
Yeah, we think that it somehow adds to visual acuity. How it works, I don't know. And so I actually haven't looked at phylogenetically who has it and who doesn't. You know what I mean? Bird-wise, do you know?
I was just reading about it last night. It's diurnal birds, but I don't know which families.
You're right. What I'll do is I'll get back to you. I'll go back. I'll look at that tonight. I'm curious about that. I wonder what families of birds have that. And that Evolution's Witness would have the best information on it. It's a really good book. He's a cornea guy at UC Davis, Ivan Schwab.
I went to his course at the academy. I don't know if he still teaches it.
He does. Yeah, he's a super interesting guy.
We have an attendee who's asking why cat pupils aren't around.
Oh, someone's asking why cats' pupils aren't around. Are they still there? Can you hear me? So I actually took the slides out. Because it was just too long. I had 2 slides on vertical pupils versus horizontal pupil. In general, if predators have vertical pupils, like a cat's eyes, right? Because they're interested in seeing things on the horizontal axis. The opposite is true. If you look at a goat's pupil, goats have horizontal pupil. It looks like a box or a rectangular square. And it's probably which detects motion more on a north-south vertical axis, meaning the orientation of your pupil detects motion perpendicular to that. Bottom line is, if you have a vertical pupil, you're a predator. If you have a horizontal pupil, you're looking for predators coming at you on the horizon and detecting motion. You're a goat or something that eats grass, basically. So my slide also had in there, when the aliens come, if the aliens have vertical pupils, run like crazy. If they have horizontal pupils, relax. Basically. I took that slide out though. I just had it in here. It's still in the slide. I think I hit it. It's because they're predators and it enables them better. And snakes have it too. I also had another interesting thing about, I don't have time for, about snake pits. Both pit vipers and rattlesnakes, pit vipers and pythons have pits around their lip, and the pit vipers have 2. Pythons and boas have it around the front lip of their mouth, and it's a super thin. So it's not sight, but the way they detect heat is through a super thin membrane. That membrane that has all these nerve cells in it is so thin that it can detect temperature gradient differences. So when they turn toward it, that pit is really seeing microscopic differences in temperature gradient variations, which is how they detect heat. So pythons and boas have it, multiple ones across their lip. Pit vipers for prey have it on their sides. So it's not eyes, but it's sort of like an eye.
We have another question. About cat vision versus dog vision.
What was the question? I'm sorry.
Cat vision versus dog vision.
Gary, do you know about cat vision versus dog vision? Let's see here. What's the difference?
I think they're both dichromats, aren't they?
They're both dichromats. So they're not they're not color vision like we have. And a dog's visual acuity, dogs, evolutionary have more rods too. So their night vision is better than ours, but their day vision, their hearing is obviously much, much better than ours, but their day vision is probably no better than ours. And their color's worse. A cat is somewhat similar, although some cats are diurnal hunters. Many are diurnal hunters and some are nocturnal hunters. So I guess I'm not sure how it would depend there. So, but most cats, at least evolutionary, are nocturnal hunters. So their day vision would probably not be any better than ours, and the color vision is worse. Good night, everybody. And again, thank you very much for participating, and stay safe. Happy holidays. Happy New Year.